function files that you're using to get the .o files, you then, sorry, I like color, by the way. You're going to notice this all throughout my slides and code is I have color prompt everywhere because I think it's boring to look at plain slides. So sorry in advance if anyone doesn't like it. So we then take our two compiled functions and create our static library. And you can list the .o files in the static library by using the flag -t. And then if you're trying to compile a code, so say we've got test code of some sort, we want to create the executable run, just follow that line by the name of the file library that you're linking to. This only works if it's sitting in the directory that you're working in. So you need to provide a path to it if it's not sitting in the directory that you're working in. So you can also use it, so you can provide the library name followed by the .a suffix, or you can use the -big L, -little l options for the GCC compiler. Okay, so that's a little bit about static libraries. I feel like they're worth to mention. The ones that we're actually going to be using and the ones that are have way more advantages are shared libraries. So the difference between static libraries, one of the differences between static libraries and shared libraries is that the library isn't loaded into the program when you're compiling it. It's just called by the program as it's executing, which means you can use different versions of libraries with your code without having to actually change the executable with your code, and we'll see that later in the lab. So in some of the folders, I provided two libraries that you can generate and that you can call either one without changing your executable. So they're loaded into a program at startup time and they're shared between programs. This allows users to update the library separately from applications that are using the libraries. So things like you might have lots of versions of GCC you might want to use, so you might have them all installed, but you'll reference the right library when you're using it, or you might have different versions of SQLAPEC or LAPEC or some of those linear algebra factors and you can reference those when you're running your code. So updating libraries, the advantage of this is you can update libraries while still maintaining the original version of the code. So you'll tend to have folders of LAPEC 108 and LAPEC 109 as they keep changing the versions of the code. So, but it means that it's backwards compatible. And you can override specific functions or libraries or even specific functions in a library. That's actually what I'm after today. Is we're going to write a library later that's going to replace some of the original MPI functions with our MPI functions and get it to do some cool things. Well, we'll try. And we can do this while the program is running. So we're going to look later at how you can just open a library in your code and find another and look up the symbol table of a function name. So we need to look at the naming conventions of libraries first. So I don't know how or how much you guys actually look at installing and looking at libraries, but they have a specific naming convention, which means that they tend to be very portable now. So the first thing that they have is an SO name, which is the special name of the library. It's the prefix lib followed by the name of the library followed by the suffix .so. So in my notation, I was using libmyfunctions.so. So the name of my library is my functions. So this is then followed by a period and a version number and incremented when the interface changes. So we've got libmyfunction.so followed by the incremental number. So if you've made major changes to your code, you might increment that number. The full SO name includes the prefix of the directory that's storing the library as well as the library name itself. But in a working system, it tends to be a symbolic link to the shared library's real name. So a lot of the time, you're going to find that the SO is actually just linking to some version of the library somewhere else. Okay. So the real name of a library is this is the file name containing the actual library code. So this is what you generate with your this is the actual code that you're generating, not just a linking name. So you add a period, a minor number, and another period, and then a release number to the end of the SO name. So you get this format here of your SO name followed by some minor number followed by the version number. So this allows for configuration control, so you can have lots of versions of the same library in your directories. So the last part then of looking at shared libraries is the linker name. So this is the name the compiler uses when it's requesting the library. Okay, so this is just the SO name without any version number. So we finished with the SO prefix. So this is the difference between the three of them. The SO number has a version number. Real name has the kind of the most recently updated version number, and then this is the name used by the compiler without any versions at all. Okay. So the reason we use these naming conventions is they help us manage our libraries. So when programs are using a library, they only call the SO name. When we're creating a library, we create a library with a real name and a more detailed version number. So every time you think you've made a significant change to your library, you would then increase the version number. And when you're installing a new version, you can install it in one of the special directories, such as lib, but you're going to most likely be storing it in user local lib. And then you can call ldconfig, and it will make a symbolic link to the most recent version of your code, or to the most recent version of the library, while maintaining the past version of the library if you need to use it. If you're not storing it in, the linker name is set up during installation. So the linker name tends to be a symbolic link to the SO name. So I have an example of that because they go around in loops. So this first example here is, just look at the standard kind of C++ library that you find in any of your home directories. The first one up here at the very top is a fully qualified SO name, including the path to the library, as well as the library name followed by the .so and the version number, which when we run ldconfig on this, when ldconfig was run on this, it's a symbolic link to the actual real name of it. So it's version 6 with working number 19. So then we also have the linker name, which is a symbolic link to the SO name. Okay, so we'll get past this in a minute just to give you an idea of the naming conventions and why we'll be doing all the compiling that we're doing later. Okay, so shared libraries, when we're creating them, we need to use a couple of flags when we're putting them together. So first we need to create the object files that go into the shared library. And when we're creating the object files that go into the shared library, we need to use the flag -fpic or -fpic with the big capital letters, okay? And what they do is they generate position independent code, okay? So this is how the libraries are able to be used by multiple programs at once, because they're not using a fixed address space. So when it's position independent code, it separates the code from the data and generates code that won't change regardless of the addresses that are being used. Position independent code accesses all constant addresses through the global offset table. And what the flags -fpic and -bigfpic do is they define the size of the global access table. This is probably more detailed than you want, but it's kind of necessary. Basically, because with the lower fpic, you have a fixed size on your global access table, and if it exceeds that, you'll have compiler errors. Whereas if you've got big fpic, there's no size on the global access table, so it always works. But the problem is it will increase the size of your library at the end. So they both have. You want to start with this one, and if you're getting errors, you then switch to this one because it'll always work. But the code will be smaller and faster if you use the lowercase. Okay, so I'm going to be using the lowercase fpic today because I'm using tiny little sample files and they're always going to work. Okay, so when we're compiling shared libraries, you need to pass the SO name to the compiler using the flags -wl. So it's a big L and a little L, or big W and a little L. So -wl passes options to the compiler that it might, or passes options along to the linker. So in this case, it's passing the name of the SO along to the linker. So these commas are important. They're not there by mistake. You don't put spaces between them. So it's -wl followed by the name of the option, followed by the name, the SO name that we're passing to the linker. So this is why I say we're defining the SO name and the real name at compile time. Okay, so we're defining our SO name here, and then this will result in the real name file being generated. Okay, -lc flag causes the linker to search the system supplied C standards for functions that you might not have in your source file. It just gets rid of some of the errors you might randomly get with compiling. Okay, so we need to generate both of our .o files. So the -fpic is deciding the size of the global offset table. -g is creating the symbol tables for each of these files. so that we can, it's creating a map between the address space and the function names in the files, as well as returning on all the warnings, and then it's just the function name. So we then follow this line here by the names of the functions we wanted included in the library. So having created a library, you need to install it. So at this point, having run the GCC -shared, we still only have the real name. We don't have the SO name, which is what we need to use for installing the library. So we'll simply, we can copy the real name file into the standard directory and use ld-config, and it'll make an SO name pointing to the most recent version of the library. You can also install it somewhere else, such as your local directories, and call ld-config on the local directory to create the SO name in that folder. Okay, so that tends to be what I would do because it's safer. So ld-config and -n is to point to a directory, and it will resolve the symbol or the SO names in that folder. And then if we want to create the linker name, or the linker name, we can create a symbolic link between the SO name and the real name, or the linker name. Okay, so we have to do that ourselves, because that's usually done in the installation process of any of these libraries you would be installing. Okay, so we now have our shared library, and it's sitting off in a folder somewhere, but we need to link it to our code the way we did with the static library. So what we do is GCC -o run test code, followed by the same notation again, the -l to point to the directory, and then the lowercase l followed by the library name. The lowercase l only works if you create that symbolic link to the linker name, the one that's just the library name followed by .so. It doesn't work if you've got a .so.6. Okay, so that's why I'm talking about all these different names. Some of these flags only work if you've got the right name in the right directory. Okay, so the program must be told the location of the shared library. So when we use static libraries, we didn't have to tell it the location of the shared library because it was loaded into the program. This time it's not loaded into the program, you have to give it the location of the library. So there's two ways we can do that. We can add the library to our LD library path. So LD library path usually stores defaults such as lib, user local lib. You can then add to that path using export. So it's an environmental variable you can add to. Or you can just throw it at the start of your executable line if you only want to do it for that one instance. We can also use a function. So LD library path adds that library to the list of libraries being checked by the program. LD preload is slightly different to that. The library that you would provide by LD preload is the first library that will be checked by the program before any other libraries are. So this is how we're going to overwrite the MPI library later. We're going to tell it to read our version of the MPI sends and MPI receives before it checks the MPI standard for the MPI sends and MPI receives. So it's going to find our symbols for that first. So that's the tweak between LD preload and LD library path. LD preload decides what's searched first. Okay. So I said most of this already. So you cannot override a function in a program with LD preload that is either implemented itself in the program or was statically linked to the program. So you can only do this for shared libraries. And you can only do it for dynamically loaded shared libraries. Symbols of preloaded libraries are bound first before the linked shared libraries. So that's why LD preload is really cool, because it gives us way more control of what libraries are loaded first. I definitely feel like you all appreciate how cool LD preload is. It's okay, I get it. So I'm gonna walk through this way too fast. So dynamically loaded libraries are slightly different. So we've been talking about linking libraries at compile time. But what if we wanted to load libraries at in our program just for a couple of lines? We want to use some random function. So we can do that in the scope of our code. So libraries can be loaded and used at any time while a program is running. They're not different in any format to static and shared libraries. The difference is how they're used by the program. So they require more work to be used. They require a bit more work because you have to add it into your code, and then your code in the executable has to be changed. But and a lot of programs don't need this much flexibility, but for what we're doing today, we're going to be using it today. So libraries aren't automatically loaded at link time or at startup, and you need the header function glfcn.h. Okay. So there's a couple of functions that we're going to be using to dynamically load libraries. So the first one is DL open. So with DL open, we provide a file name, which is a link to, it's a string listing the library that you want to load from, and then a flag. And what the flag does is it either LTLD or TLD lazy or TLD now, which basically means the first one resolves undefined symbols as the code is being executed, and the second one resolves undefined symbols when at the very beginning, and if it fails, it won't continue any further. So RTLD now takes longer, but you're not likely to get a weird error in the middle. Okay, we've then got DL sim and DL. I think that should be DL close, not D close. And what DL sim will do is it'll take the handle, which is the link, is the pointer to the library that you opened, and it'll look up the symbol so that the symbol is the name of the function that you want to use. So you either have malloc or free or some other function that you want to look up. And then the DL close just closes the library that you've opened within your code. You need to use the flag minus LDL, and I put this in here mostly because I keep forgetting to use it when I'm compiling stuff with this library. So that when you're creating the library, or when you're creating the shared library, you need to throw the flag minus LDL for these functions to work at the end. Okay. So this is an example from the man page of DL open, and it was short and sweet, so I stuck on the slides so we talked through it. So this is the plan here is to, instead of linking to the maths library, we just wanted the one function cosine from the maths library. So we opened the maths library, found the symbol for it, and closed the maths library again. So what's happening here is you have to define, so you need to know what the function looks like at the beginning. So we know that the cosine function takes the double as its argument, so we need to declare a function pointer at the beginning for cosine that we're to store the pointer to the function that we're going to look up. And here we're going to use DL open to open the maths library lib.lib.7.6, which is stored in one of the default libraries. And we're opening this library with RTLD lazy, so it will resolve the symbol tables as we go along. So we're not going to worry too much about that. And then this package also has error checking, so if you call DL error, it'll tell you whether or not this call to the handle was successful or not. And what we can do then is we can say we want the cosine function, and we're going to use DL symbol to look up the symbol for cosine. And we're going to say look up in the handle, so we're going to look up in the folder, and we're looking for the function, the symbol to find its cause. So we know it's in the maths library, so this example should work. So we know it's in the maths library, so it knows to look it up. And so now cosine will represent the cos function that we would usually use in the maths library. And then you can do error checking to make sure that this works again, and it's good to throw the error checking in, because if it doesn't work, it just crops out and gives you a segmentation fault. It doesn't tell you anything. And I say this because I was looking at it about 1 o'clock last night, and I was like, why is this not working? Okay. So it's good to throw the error checking in, especially when they give you the error function for it. And then if you print the results from this, it will give you the normal answer for the cosine. So you might not appreciate this. I think this is super cool because you can. It's what I use this type of code for, where you create wrappers around functions. Is for you can add your, so later on in the tutorial we're gonna write our own malloc and write our own free. And you might ask, why would we write our own malloc and write our own free? It's because you can add in counters and running totals and that type of thing, where, okay, how many, so if you've got this giant program, you might want, and you don't know how many, you don't want to maybe run Valgrind or something on it, but you know there's something wrong with it. You can kind of keep track on your mallocs and your frees and make sure you're actually freeing everything you've allocated. You can keep a running total on the size of, so the amount of memory that you've been using. What else have I done with this before?
yeah, what I usually do is, especially because I work with quite large sparse matrices that I then invert so they become dense. It's really helpful for keeping track of the amount of memory you're using either at one given time or in total. So it's just for getting more control over your code that you might never possibly want, but I do. So I'm a control freak with my code. So this is an example of how you use the DLSim handle. So this is I introduced this because MPI gives us this profiling layer to it that allows us to call MPI functions from within function wrappers, but not all libraries give us that functionality. So you need to find a way of looking up the original symbol of the function that you're trying to use without having to load the entire library. So you can open it, call it, and close it again, and it's nice and neat. Okay. So I'm way too fast today, which is problematic. So I had problems. I had a tarball on my site for you to look at in the lab later on, and there's a couple of different folders. There's going to be a static folder, a shared folder, DLL, and a malloc folder. The DLL just has that cosine example if you want to try, compile it, and run it and see does it work. The static and shared libraries are for you to be practicing with how to link shared libraries and static libraries if you've never practiced really with that before, and then how to get them to run with a test code. And then the final example is getting malloc to be replaced by your own function wrappers for it, and you can add in whatever you want to it. So you can add in some stupid print that says, yay, my malloc works, or you can actually get it to do something sensible like count how many mallocs it's running or how many frees it's doing. So, and those are references for stuff I was wrong on it. So yeah, sorry, way too fast this morning. So you can go back to sleep for 20 minutes for the coffee room. Does anyone have any questions? Or wonder why I do this at all, because I find it really interesting, but other people probably have no time for it at all.
For instance, what do you expect here for UTD with the malloc? And do the same defining a macro and doing this stuff with macro?
Yeah, it's just another way of doing it.
Okay.
It's just, it gave me more functionality with what I could look at and store and that type of thing. So, the reason I've done it this way is because of the way I did my thesis, where I was creating wrappers and I was trying to create a profiler for MPI, and you needed to do it that way to get more control over the information. So you needed it for adding things to W linked lists and that type of thing. So it just gave me more control that way.
How complicated can you get your macros to be? I mean, are you doing them just as preprocessor direct? So hash define malloc to be something that then also calls malloc kind of thing, or how complicated? Because I guess the thing that's nice about doing it this way is once you've decided that you're going to replace the function called malloc, you can then add as much code as you want to your version of malloc before it actually allocates the memory for you. So is there a complexity limit on what you're coming up against? Is it? So I mean, is it maybe? I mean, it's not required. I mean, this is one way, and sort of this is the approach that tools like Valgrind and Electric Fence and things take to give them all the functionality. Because have people used Electric Fence before? Because Electric Fence is really useful because it shows the way it works is it realigns your memory allocation so that the end of your array comes at the end of a page in memory. And so as soon as you go over the beginning of the next page, you immediately get a segmentation fault. Where a lot of the time, if you do a for loop, you say for I equals 1 to 10 over an array, and then you go to 11, it'll probably still work. It might override a value, but it won't necessarily. It'll corrupt your memory, but it won't give you an error, and because it's still all within one page. Where Electric Fence does replace all the malloc calls by changing your alignments of things in memory, so it gives you the power to say, ooh, here's where the error exactly occurs. And it's the same sort of thing. But you can replace you can write your own version of every function if you're really crazy.
You could make it return null for every time you try to malloc someone and try to replace somebody else's code and really annoy them. That would be mean.
Yeah, that'd be good.
Yeah, can you replace malloc?
Replace the system called malloc with return null. and then everything's code.
No one's code will ever work again. The thing with the for loops, I was doing a class on debugging for someone, and they were like, "So how far does the for loop go?" And I ran a for loop that was allocated for 10,000, and it made it as far as 40,000 before it even thought about crapping out. So
Yeah, and usually the problem is like if you're just doing a simple example where you just go malloc something and then run over the end, but it doesn't matter. But if you've got a malloc and then another malloc, or and then so your second data structure ends up beside your first one, and you just keep plowing through and corrupting your values. It
doesn't give you an error, but you don't have right values either.
Yeah, you just silently corrupt all sorts of other things, or you run up the stack or something like that.
Anyone have any other questions? Other than why we do this, because I can't really justify that other than I did this was my project and I thought it was great at the time, so it was pretty good.
Yeah, where you really see the stuff come in when we actually start using these techniques with the libraries to go in and replace all of the MPI, or not all, but some of the MPI functions with additional information. So every time you do a send, you can tag it with a certain thing and then track where it's going, and then you can discover where your MPI code is failing you, or where you've got mismatches between where your sends occur and where your receives occur, which then gives you quite a powerful tool for then saying, this code isn't very efficient, I should totally fix it because here's where all of my problems come from.
Because we all write really bad code, but we don't even realize it. Like, it's definitely worth running your code through some of these packages that people have out there, because you look at the results and realize, I'm waiting, how long is that barrier function for something else to turn up? And it gives you lots of information. But we can talk about that later, because I have lots of pretty pictures to show you about wait states.
Lots of games use dynamically loaded libraries. What would be, why would they do so? And what are the advantages of dynamically loaded libraries compared to statically loaded?
Well, dynamically loaded libraries can be changed without changing the code itself. So when we're using static libraries, we link them at compile time. So we say, GCC -o run, and we follow it by the library name. But what we do with shared libraries is we do add the library name to the compile line, but the library that's loaded is loaded at execute time. Okay. So when we run the program, it looks for the library. So you will compile perfectly fine if you put the right flags in, but you might only get an error that says we can't find the library when you run the code. So you need to then link it to where the library is stored, because it knows that the address of the library is not fixed. It could be any version of the library if you provide the right SO name, because the SO name could be pointing to any version of the library. So the advantage I would imagine the gamers guys get is that they have the game and the libraries, and they're almost two separate things. The game is still there, but the libraries are changing for the game. So that would be my guess of what they're up to. It gives you a lot more flexibility with it. So this is why, we can load different versions of MPI with our code, because they're shared libraries, and that we load them. We say, yes, we want to compile with MPI, but the location of the MPI can change. You could have OpenMPI stored here, or you could have Intel MPI stored here. And depending on what's been loaded in your modules is the one that's used by the executable. It's not just one MPI stored in one folder. So I tend to try, the advantage of it is, like, I get to run my code with OpenMPI and Intel MPI and see, do they give me the same errors? Do they give me the same answers? Is one faster than the other? So you get more flexibility as the user by getting to use different libraries.
Do you have to recompile each time you change the library?
No, you have to. So the executable can stay as it is. But if you use static libraries, yes, but dynamically loaded, no. So and that's why that's the major advantage of them then, is that you have your code and it can stay the same, and you could change your modules and it could give you different results.
Yeah.
And so you can do a lot of playing around with. If you go back to the slides, when you had your LD, where is it gone to?
Isn't it?
things like LD, all these sort of things allow you to modify the execution of your code massively just by changing the order in which these symbols get resolved from here. So when the executable comes to a thing, it goes, oh, here's a function I need to call. I should be using this dynamic library, but if you've changed where that library should, where the order and places it should look, you know, it can run the right version, the test version, the newer version, but for programs that are really large and take 6 hours to compile, which in the HPC world is not unknown, this can be a much quicker way to test out, you know, new functionality and things like that. Because you just recompile the libraries, so a small section of it, rather than, you know, if people build proper makefiles, you would still have to rebuild one bit of your code and then relink your executable. But so many programs now, if you change one source code, it goes, I'll rebuild the whole lot just because people don't write proper makefiles. So,
That's true.
so yeah, you can have a fight. Write proper makefiles or use dynamic libraries. Which is an easier thing to solve. It's probably easier to do some of these things.
That said, later I've only provided one makefile in any of the folders I've given you, so but I gave readmes with them, like, this is how you compile this stuff, so it's fine. Just because I was getting lost myself and trying to remember how to compile each different type of library. So.
Is there any real benefit of using lazy loading compared to year one? Because, well, anyway, when we initialize the program, there is like some time overhead that we just spend for allocation data structures, initializing all the objects. So maybe we can just use either load in this case.
Yeah, but the whole point is it gets to that line and then loads the library. It's not loaded from the very beginning. So the loading of the library then kind of happens around that point in the code. It doesn't necessarily.
Yeah, this means that the first call to the library will take quite a long time.
Yes, one of them loads the symbol tables faster than the other, so it's just, I think one is shorter, one is slower, but one makes the code bigger. Yeah, sorry, I don't know the difference between the two of them well enough to justify either of them. So.
But I suppose the other problem as well is if you use the either one, it will load every possible symbol and every possible point at the start, because it can't know until it calls the code later on whether the things are going to get executed. So you may, at the start of your program, load resolve thousands and thousands and thousands of symbols, potentially, and then never call them in your code. So if you're only going to call one of the functions out of 10,000 functions in a library, which is, you know, that's also where the trade-off comes.
Okay, so it also helps to save memory.
Yeah, because you don't have a footprint of, here are all these functions that I'm never going to use, but because they were in the library, and if you're linking with 10 dynamic libraries, and then each of them has 1,000 calls, and each of them also, it starts to take time to resolve them all. The memory footprint isn't such a big problem. I mean, it's a pointer, so it's no really, it's a little overhead, and it's more the having to go through all the library files, find them all, as opposed to just finding the one that you need at the time that you need it. So, I'll try one of them.
Anyone else got any questions? No? Okay, that's okay. We made it 5 to 11, we did well.
So it's easier to have
Coffee would be good.
Okay, I'll just leave the webpage up there.
That's the site for later on. The 2 slides, this morning's and this afternoon's slides are there, and then there's a tarball for the morning and the evening as well. Just little bits of code that you might want to play with.
coffee.
Yeah, so then it says, it's not available to me. Yeah, I don't think that's. This is 30 slides, I think it's 20 minutes.
So, is there an advantage? Well, I don't know.
I'll just inside the result.